Hello, Professor. My name is Nathaniel Fedida, and I will be presenting to you my student work review number two. Now, I worked on two specific use cases. First use case is for the fleeing behavior for the agents. And this use case has to do with implementing the behavior for the agents to run away or flee from hostile NPCs as soon as these NPCs come into range or proximity with our agents. The second use case is the map encoding. Now, the map encoder, um, what it does is that every single agent takes in its own rendition of the map of the landscape, and it passes it into the backend. And once it's in the backend, the large language model takes in this map and it analyzes it using a library called Pydantic AI. And once the LLM has an understanding of the map and where everything is positioned on the map, such as where the agents are, where food is, where the hostile NPCs are located, it's able to use that as information to determine what the agent's next decisions will be. Now, I will start with the fleeing behavior. And so essentially, to start off, we just have these headers and these different settings, such as the flee radius and the flee speed. Flee radius having to do with the proximity at which the hostile NPC meets the agent, and it's essentially at what space between the two will the agent then um, proceed with running away. So I'll show these in the simulation. Flee speed has to do with how fast the agent runs away from the hostile NPC. And for Predator Tag, this is where we get all the prefabs or the hostile NPCs, where their tag is specifically marked as enemy agent. And then next, we get the rigid body of the agents and the hostile NPCs. This is just a Unity thing in order to sense whether or not something is an agent or a hostile NPC. The body needs to have a component to it called a rigid body. And now for our initialize, we have a quick check where we make sure that the prefab has a rigid body. If it doesn't, then we pass in an error. And in our update function, we're essentially repeatedly calling flee from predators, which is the meat and potatoes of this script. And the way it works is that we use hit colliders, which uses Unity's built-in physics library, to essentially check for predators within that specific set radius that we set at the top here. And essentially, we check to see if that uh, object that the agent has collided with, if it contains the predator tag, the predator tag being the enemy agent. We essentially confirm that, and if it is in fact an enemy agent that the friendly agent has ran into, then we proceed with this code, which essentially calculates what direction the agent should run away from using vectors and position transforming. And predators that are closer, like we see here, predators that are closer will have more of an influence. Now for this section, this essentially has to do with how fast the agent runs away. We calculate different things like fleeing velocity. We take the current direction and we multiply that by the flee speed. And essentially, the higher that value, the faster the agent runs away. And so let me show you how that looks like in the simulation. The purple agent is the hostile NPC. This is what the agent will be running away from. And the blue box here is the agent. Now, it's important to note that I marked this use case as 50% completed. And the reason why, which you will see in a second, is because the agent doesn't fully run away yet or flee. It more keeps its distance away from the hostile NPC. And let me show you how this looks like when we run the simulation. Now you'll see here, as soon as this agent comes to the right, you'll notice that the agent is running away. It's always keeping a specific distance. Now, the only issue is that it slightly follows the hostile NPC. That's something I'm yet to fix. But for the most part, the agent knows to keep its distance from a hostile NPC the instant the hostile NPC enters a specific radius. Okay, and so for the next use case, we have the map encoder. Now, the way the map encoder works is that we initialize certain objects and variables. We have the map camera, we have the width and the height of the 2D map, and then we have the server URL, which is the backend. This is the URL that all the requests and the information, such as the encoded map, will be sent to. We have a texture, and then finally we initialize an HTTP client. This is what we use for communication. We initialize a class called map payload, and in map payload there are two important things that we need to have. One is the agent ID, so this refers to which agent is the one passing their map. And the next one is the map in the form of base64 encoding. Now the first function we have is the capture and the send map. In capture and send map, we first run the capture and encode map function, which I'll show you in a second. We take the map image, we convert it to a base64, and we keep it in this variable. Next, we check if this variable is null or empty. Otherwise, we then send the map to the server. We pass in the agent ID. So in this case, it's agent three's map, for example, that is being sent to the LLM. And here in capture and encode map, what we do is we first make sure that there's a map camera assigned, because if there isn't, there's no map to take in and encode. And we grab that map camera, we render its texture, and once we render its texture, we read pixels using Unity's built-in functions, and this is essentially what converts the map into that long encoded base64 string that you will see in just a second. Next, we encode that map. We encode it to PNG, um, and we then take that PNG data and we convert it to base64 string. And then lastly, we simply take that and we send the map to the server. So we take in the agent ID, and then we grab also its map in base64 form, and we just run it through a map payload, where we send in this encoding along with some HTTP response messages, and we check to see if everything went well. If the map was sent successfully by the agent, then we run that. Otherwise, it's a failure. And let me now show you how that looks like. So we have the map here. Now you will see here that we get logs that say update LLM set to true. And now every single agent reports back that the map has been captured and sent. Now, in order to see how this looks like, if we go back into the backend, we will see these long encoded strings. These each and every one of these refers to every single agent's version of the encoded map.